In this question, we have two particles with two masses there, and the string is taut, and P is vertically above Q. That's a very important part. The force is 10 newtons. And as per usual with these questions, you're finding acceleration and tension between the aspects of the string. And there's a few questions here today that we'll be doing that. Part A especially, the first part, is almost always finding those two aspects for the connected particles. So I'll just draw this now, P and Q. So it's vertically above Q. Be careful with that detail. Put in the weight and the tension is going up. So we put that in as well now in a second. So we're going to do two equations, one for P and one for Q. You can cancel out your tensions, and then I suppose it's a form of a simultaneous equation. You're going to get a new equation. Often with these questions, you're doing two individual components, and then you'll find like the whole system. Or you could do the whole system in one go, but it's that kind of idea with this particular topic. So P, the equation for P, so we have 10 and then minus everything else. So 10 minus 0.5 G minus our tension is equal to MA. So force is equal to MA Q. Be careful here, just think it's T minus 0.3 G. And is equal to MA again, so 0.3A. So there are equations. We can call them 1 and 2 if you want. And we're going to cancel out the tensions of the system. And so we'll end up with one equation, which we'll do now. So just check in there now. Yeah. So minus T and T. And so with simultaneous equations, just remember, if you have the same sign, you'd subtract. So we've different signs here, so we add them. So you're always adding them in this kind of question. So A is equal to 0.8 over 2, which is 2.5 meters per second. So always, when you find the acceleration, you're going to substitute it back into one of your equations, in this case P or Q. I'm just going to pick the second one, which is T minus 0.3 G is equal to 0.3 times our 2.5. And from there you find the tension. .75 newtons. And that's our question 2 on June 2022. Found the acceleration and the tension in that string. In this question, we have two blocks on an incline. Two masses there of 4 kilograms and 5 kilograms. It's a light, inextensible string. It's a smooth plane, so there's no friction. An angle of tan, 7/24. And we have a force of magnitude 36 newtons acting on our B block there. So we're also given details about the line of greatest slope and so on. We'll get to that. So again, as often, find the acceleration and the tension in the string, and then there's a follow-up question on that. First of all, just tan 7/24 is, you can put into 16.26 from your calculator if you want, but really it doesn't make a difference. But you're given tan, and yet we use sine and cosine components. So just using Pythagoras here, we get 25 for our hypotenuse. So of course, sine would be 7/25 and cosine would be 24/25 for those component parts. So now just adding to our diagram for our blocks. So the weight there and the perpendicular components. And we're going to do the usual thing. We're going to prepare two equations for A and B. You could do the whole system as well. You can do it whatever order you want. But make sure you do the individual components and then the whole system just check it from there. There is our tension in the center, and the arrows just take note of the way that works there. So tension in the string. So now we're going to start the equations. Yeah, the tension goes that way. Okay. So A, so starting off T, so if you split up the two of these blocks in a way, you'll see that our leading force for A is T. So T minus 4G times 7/25 for the sine component, which is parallel to the slope, is equal to 4A. And B, you'll have 36 minus T, or minus 5G times 7/25, whatever order you want. 36 minus those two forces is equal to 5A. Again, F equals ma. So cancelling out the tensions of the system, we'll get the whole system. Again, with simultaneous equations, just a different sign. So you add the other components. So 36 minus 4G, 7/25, minus your 5G times 7/25 is equal to 9A. So put them all together on the left-hand side, divide by 9, and you'll get your acceleration. Acceleration is 1.2 meters per second. Once again, substitute in your acceleration to one of your equations, A or B. Plug it into A. So we just with my convention, just call them 1 and 2. So equation 1, equation 2. And we call it equation 1. T minus 4G times 7/25. Again, you can simplify these parts as you go along. I'm just making it visually consistent. It's equal to 4 times 1.2, and you'll get your tension then. So the tension is 16 newtons. That's part 1 complete. Now on to our second part. At a particular instant, speed is 1 meter per second. Think of the word instant. It comes up quite a lot actually. So at this instant, or from this instant, and obviously to me, it means that in terms of your suvat or your equations of constant acceleration, speed in this case is u, not v. It's the beginning of some motion. And we're going to find the time to see how it moved. So it moved 0.65 meters. Our initial velocity is 1. And our acceleration was 1.2 from the previous part. And we're looking for time. So there are actually 2 ways you could do this. Often there are 2. You're given enough details if there's not too many unknown variables. So we're given S, we've U, we've A, and we've defined T. You could use S equals UT plus half AT squared, or as I'm doing, just V squared equals U squared plus 2AS. But this particular one does not have time, so I'm finding the velocity first. The velocity was 1.6. And now I'm going to use the trapezium formula. So S equals half. So U plus V times T. Which your trapezium would be half A plus B times H or something like that, but it's the same kind of formula. Once you multiply and find that out, it's a little bit easier to calculate. So 0.5 seconds. The other way I suggested earlier with s equals ut plus half at squared, it would have been a quadratic, so it's a little bit more difficult to do. So there's our answer. Time was 0.5 seconds. Okay, so we're looking at a car of mass 1,200 kilograms with a trailer of mass 800 kilograms. We've got a hill, so I've got a little picture here set up already. And we'll put in those details now. This is our first rod question, we'd say. So mostly you'll get string questions. Pulleys and strings are kind of the same thing. And other details are sine value of 0.1. Driving force, and we have resistance for both objects. And again, once again, find the acceleration and the tension. So finding acceleration in the system and a tension in the tow bar in this case. So putting your tensions there as well. You may do a separate diagram from both if you wish. After a little bit of practice, you should be able to see the difference between the whole system and the individual components. Okay. We start again, the same idea of putting our equations together. So we have an inverse sine of 0.1, and we'll just set up now the parallel or perpendicular components. The sine value is 0.1, so for that component parallel to the slope, we will be using that. So just make note of it and make sure it's clear. First one, I'm going to do the whole system first, so parallel to it all. So parallel to the slope, the incline. So our first driving force is 2,500 minus then 2,000 g times 0.1. So 2,000 is the total mass. And then 0.1. And then minus our 300 and 100 is 400. So there are forces involved is equal to 2,000 A. So F equals ma. And from there, basically, you can find the acceleration. So 0.05 meters per second per second. I would usually tell students to do the individual components for the car and the tow bar at that point, as well as the whole system. But either way, we're going to do it now. So we're going to find the tension in the tow bar. You just have to pick whether you want to use the car or the trailer in this case. I'm going to do both, just to make it very clear. So the individual components, our car has a driving force of 2,500 minus the T, just check those bits and pieces, minus 300 resistance, and then minus the sine component, 1,200 G times 0.1. You might have noticed by now that G times 0.1 cancel each other out if you did it that way. It's equal to 1,200 times 0.05, which is our acceleration. And again, the trailer will do the same. What's its driving force? Well, it's kind of it just has a T at the front there, connecting to the first particle of the car. So T minus 100 minus 800 G times 0.1 is equal to 800 times 0.05. And again, do either one or both, and you'll get the same answer for the tension. And the tension is 940. So when we're doing these kind of questions, you'll notice we have a rod. This is called a rod question. It's quite different to the string questions in a way, because it won't generally change direction And you have other aspects of strings where they might be taut or have slack or be in tension like that way. And another thing is actually that the force in a string can never be a thrust. So you only have tension. Again, remember we have modeling assumptions with these ideas as well. Part B. We've given a speed and the driving force becomes 0. Find the time in seconds before it comes to rest and also the force in the tow bar during that time. So go back to our first equation for the whole system. Really what's happening here is the driving force of 2,500, it disappears. It becomes 0. But everything else remains the same. Everything else except the acceleration, of course. And if you think about it, your acceleration should be negative. It should be a deceleration. So just wiped out the 2,500, driving force is 0. Redo that calculation for A, and you'll get minus 1.2 meters per second. Our next part, we have an initial velocity, because when it's traveling at that point, starting, at the instant, those words come up, u is 30, v will be 0 because it comes to rest. So do your suvat, if you wish. And I think we'll use v equals u plus at, yeah. So 0 equals 30 plus minus, you can just say minus 1.2 t, and you'll get a time of 25 seconds. So we found the time there for the system when it comes to rest. And now the force on the tow bar, we'll fit it in here at the bottom maybe, on the right hand side. Go back to your equation for your force, for your trailer, and plug in our new acceleration. So you have t minus 100, do resistance, minus the 800g times 0.1, that's 100, yeah, minus 800 g times 0.1 is equal to 800 times minus 1.2. That should give us our tension there. It should be negative. Yeah. So T is equal to minus 60 N. Minus 60 newtons. Back to our pulleys or strings. So we have two particles, 0.3 kilogram and 0.2 kilograms for both P and Q. It's fixed, smooth pulley, so no friction. We're at an angle of sine 3/5. And we've other details there about the height, which you can see on the diagram. And just check all those little details about what it says about horizontal or vertical aspects. But you should be accustomed to a few of these questions as you go along, and you'll see how they work. They become quite similar. And hopefully they become more familiar. So I'm just doing out the sine values there. You can just do a triangle if you want. You can use your calculator. You have your calculator, so. But from pure one, you should probably know this kind of stuff anyway. When you're given a sine, tan, or cosine value, you can figure out the others using your triangle there. But the hypotenuse there was 5, and the opposite was 3. So using Pythagorean theorem, we found 4. So cosine would be 4/5, for instance. So now we're going to set up our question. We've got P and Q. So again, doing the individual components and the whole system in whatever order you want. So the diagram, just putting in our tensions and laying out any components that need to be put in. P will have a little bit extra, and Q will be straightforward enough because it's hanging freely. And remember, it's a closed system, so the tensions on both sides are equal, so they always cancel out, as you've seen in 2 previous questions in this video with strings or pulleys. So P, you got T minus 0.3 G times 3/5. So that sine component that's parallel to the incline. So that's our force. There are forces equal to 0.3 A. F equals ma. Q, so Q is hanging, so you'll have 0.2 G minus your T is equal to 0.2 A. And again, you can see, as always with these questions, your T's will cancel out in terms of simultaneous equation, and you'll add the rest of it. And we call our equations 1 and 2. And so we have 0.2 G. I'm going to just calculate that one out. It's 0.18 G. 3/5 of 3, 0 to 0, equal to 0.5 A. And our acceleration is a positive 0.4 meters per second per second. That's our first part. And again, as always, you'll plug it back in or substitute the acceleration into one of your equations, 1 or 2. In this case, I'll pick 1. Equation 1. T minus, I'll put in that 0.18 G, it's just simplified, is equal to 0.3 times 0.4, the acceleration. I'll just fix that. 0.4, yeah. So our tension is 1.92 newtons. That's our first part done. We've 2 more parts now. You'll notice, if you have, this is question 7. So in this particular year, 2019, it was the last question on the paper. So again, it's going to have some expansive aspects, which is why we're doing it. So Q hits the floor and doesn't bounce. So you can think about it, what happens, like Q is going down, and P is going up the hill, but it doesn't reach the pulley. Find the time. Again, the word instant. From the instant P is released for Q to reach the floor. So that's our first of the 2 second parts that are more about, what's actually going on in the question. You kind of have to interpret the question. It's more difficult than the usual things we do, using formulas and so on. But we do get to use suvat. So let's put in our details. We have 0.8 for the distance. It said the instant, so we know that our initial velocity is 0, and we have already an acceleration of 0.4, and we can put that together in our generally the most popular, the most common formula from constant acceleration, which is s equals ut plus half at squared. Put in our acceleration there, and you get a nice whole number of 2, so the time is 2 seconds. So part 3, Q hits the ground and the string becomes slack loose. Find the time from the instant at which P is released for the string to become taut, or tight again. Take note of those words. There'll be keywords that might pop up now and then. Slack and taut. So we're going to do another round of suvat, I expect. Again, just think about what is happening here. The particle is kind of moving up and going back then, but it's not actually moving. I think the distance will still be 0. It kind of pops up and back on that line in an instant. So we're going to find P, so we'll be definitely going back to that equation for P that we did originally. And I think suvat will help us as well. So let's look at P first. So the tension has disappeared, basically. So we've minus 0.3g times 3 over 5. So back to the first equation that you've seen that we did, at the top left. And that's equal to 0.3a. So from that we get our acceleration. So minus 6 meters per second per second. From there we can move on to the suvat, I'd say. So we have initial velocity, which was 0. Time is 2 seconds. I'm going to plug in, I'm going to find velocity as well. So u plus at, so 0 plus 0.4 times 2, that would be 0.8. Okay, so doing it out, just lay it out first. So 0 there. Time is 2. We want to find our velocity as well. There might be another way of doing it. But anyway, this way works. V equals u plus at, so 0.4 times 2 is correct there. So our velocity will be 0.8 for that first movement, we'll say. So we've got 2 stages. Sometimes this happens in these questions. I've noticed it from Unit 1, when you had multiple stages, or more than one stage, when you're doing questions involving velocity, displacement, and acceleration. But generally, I think in this course is a velocity time graph. So again, we'll do our suvat again. So the initial velocity was 0, and we just calculated our velocity of 0.8 meters per second, which becomes our initial velocity in the next stage. Have a think about that before we move on. So 0 is equal to 0.8t plus half. Half times minus 6t squared. Yeah. We're going to have a quadratic, but you can ease it out. So minus 3t squared plus 0.8t equals 0. Factor out the t, as I'm doing here, and you'll get an easier way of it. So t equals 0.266 and so on. So our final answer, of course, is we had 2 seconds for a previous movement when q hit the ground, and now we have a 0.27, we'll just round it. When q hits the ground, it is a slack, and then it gets taut again. So the total time for that was 2.27. Looking at 2 strings, we've got a particle P, okay. It's vertically upwards, as we can see in the picture. Diagram 0.3, okay. And so we've got also lengths given from A to B. And I do the details you can see in the diagram anyway. So find the tension in each of the strings. Remember, it's a closed system, so the tensions, the tension will be equal on both sides. So the way to do this question is to, of course, put in your little details like tension there. But moreover, we have a triangle, and we have other tricks in our arsenal. So find the angles, using your trigonometry here. So of course, tan is opposite over adjacent. We know our hypotenuse is across from our right-angled aspect there. On the diagram you can see it. So just find that part first. So we find our angle for tan, which is 53.1. So I'll just start up the equation. Again, the hypotenuse is there, so it's across from the right angle. We want to find the tension, so we're going to create our equations as usual. So horizontal and then vertical. So we've got tension in A, cosine So it's cosine 53.1 is equal, so we'll find the other angle as well there. So it's 36.9. So 36.9. Maybe I should put in the little details just to make sure. So of course, knowing that we have a triangle, you've got your 53.1 degrees, you've got your 90 degrees, and of course, subtract them from 180 to find what we said. So 36.9. Okay, just making sure. So T, tension in B is cosine 36.9. And we can simplify that by dividing one over the other. So TA is equal to 1.332 TB, tension in B. So that's our first equation. We'll leave that there. And we'll do the vertical component. Okay. So resolving it vertically, TA sine 53.1 plus the tension is in B as well. So sine 53.1 plus tension of 36.9 plus the weight of 3. So plus 3G. And it's equal to our force, which is 5 newtons. And from there you can simplify like 5, cancel your 3 on both sides, you'll get equal to 2. So we end up with 0.8 T for A plus 0.6 T for B is equal to 2. That's our second equation. And now we can substitute equation 1 into equation 2. So 0.8 times your 1.332 T for B plus 0.6 T for B is equal to 2. And once you simplify that down, you should be able to get them. So let me just see it, 1.6656 T is equal to 2, so you just divide it. So divide both sides by that, and you get nice round numbers as well. So TB we get first there. So 1.6656 TB is equal to 2, so TB equals 1.2 newtons. And then last part, just substitute back in again into one of your equations. So you might get tension in A is equal to 1.2 times the 1.332. That's the simplest way to do it. Or 1.332 times 1.2, same. Is equal to 1.6 newtons. And that's our tension for both A and B.